moving on to chemical kinetics, or should I say moving back to chemical kinetics. The very first topic we talked about in General Chemistry 2 is kinetics. At that time, we talked about kinetics a very small bit, only enough so that we could say equilibrium, chemical equilibrium, is defined as when the rate of the forward reaction is equal to the rate of the reverse reaction. At that time, we saw plots like these, and we could draw a line and say when the plot gets level, equilibrium has been established, and so we called the region to the right the equilibrium region. Everything over here we called the kinetic region because that's where concentration was changing. When concentration is changing, you're in the kinetic region. When concentration is constant, you're in the equilibrium region. Even then, when we saw plots like this, we were able to determine that this is a reactant because the concentration is decreasing, and so is this. While this is a product because the concentration is increasing. So if you match that up to the little letters, A and B are reactants and C is a product. We even have already been tested on how to determine the exact equation looking at a plot like this. Maybe you should revisit that. It was one of our first things we did way back then. You may or may not have noticed, but the y-axis was not moles. The y-axis was concentration. Why might we use concentration to compare reaction rates instead of moles? Well, in order for a reaction to happen, molecules must collide. So if you have this many molecules and you put them into a larger container, some sort of larger container, they're less concentrated. What does that matter? Well, in the smaller container, those molecules will collide more frequently than they will in the big container. They're more concentrated in the small container than they are in the big container. So the number of molecules matters because that affects the number of collisions, but the concentration is the factor that we will see affecting the collisions most because concentration includes the number of molecules and the size of the container, the size that those molecules are allowed to move around in. Here's an example of a reaction that one can measure the kinetics of. And if we were able to do our lab experiments, we would be doing something very similar to this. Slightly different, but very similar to this. What's cool about this reaction is Br2 up here, which is one of your reactants, is a reddish colored compound. This guy here, you don't have to know him by name, but he's formic acid. When Br2 and formic acid react together, they make these products, which are all colorless species. So if you look at the concentration from here to here to here to there, the concentration of Br2, the red stuff, is apparently decreasing over time. And you can see that with your eyeball, but you can also see it with a chemical instrument. So one can shine a light of a certain wavelength through your sample and detect the absorbance of your sample. Over time, the absorbance of your sample will change because the color of your sample disappears. I sort of said that in a backwards way. As the color disappears, it no longer absorbs light, so you can take the maximum amount of absorbance here, and you can plot that on a separate plot, absorbance versus time. That says the concentration of bromine is proportional to the absorption. So if we plot absorbance versus time, in the beginning, it will absorb the most amount of light, but over time, that absorbance decreases. So had we been able to run an experiment like this, we would not have been able to detect this many points along the way. We would have gotten a starting point and an ending point and made some assumptions about the middle. But we would be collecting this data in order to determine the rate law of a given equation. So you may not remember, but we've mentioned a rate law once before. A rate law is a formula that's used to find the rate of a given reaction. Here's a reaction. There's my plot of how concentration of my reactant changes over time. So I can find the slope of the line at various points, and that's what these 2 points that are in pink have done. They've found the slope of the line at those 2 points. Note the slope of the line is different at those 2 points. So a rate law is always written in terms of reactant concentration. So we are going to write a rate law for this reaction. So let's remind you of what a rate law looks like. The rate law says rate equals something. That something is always reactants. The rate of the reaction is always dependent on the concentration of the reactants. So we'll stick the reactant concentration in there. That reactant concentration is always multiplied by some K value. Note, I know it's not a big deal to y'all, but this is a little k, small k. Big K in chemistry is equilibrium constant K. Little k is rate constant K. So a rate law says rate equals K, rate constant, times the concentration of reactants raised to some power. That some power is a whole number, typically, that's often not greater than 2. So that could be a 0, a 1, or a 2. Okay, cool. This is a rate law. If this is a first order reaction, that would mean X equals 1. It would be rate equals K times concentration of N2O5 to the first power. Okay, turns out this is a first order reaction. So seeing this, number 1, is how I know it's a first order reaction. That N2O5 is raised to the first power. So using some other experiments, this rate constant has been solved for already to give us 6.2 times 10 to the negative 4 seconds to the minus 1. Note the units on the rate constant. We'll talk about that guy. If we tried to solve for the rate of the reaction at 0.44, that's this line up here, 0.44, we would multiply 0.44, the concentration, by our rate constant, and we get 2.7 times 10 to the negative 4th molarity per second. All that is that's telling you the slope of the line at that point. If we had solved for something up here, like maybe 0.9-ish, we would have gotten 5.4 times 10 to the negative 4. You could actually set the rate equal to that and solve for at what concentration does the rate equal that, but we're not going to. So I've already sort of said this, but a rate law expresses the relationship of the rate of the reaction and the rate constant and the concentration of the reactants, definitely reactants raised to some power. So if I'm given this equation, I can write the following rate law. How do I know this should have been a 2 and that should have been a 1? I don't. I'm just trying to show you what a rate law looks like. A rate law is rate equals K, little k, times the concentration of A squared times the concentration of B to the first power. Why are only A and B involved? Because it's only in terms of the reactant. And I'm giving you a 2 and a 1 so that I can say that we would say, looking at this rate law, the reaction is second order in A, the reaction is first order in B because that's a 1, and we would say the reaction is third order overall because you sum together those exponents to get your overall rate law. So the rate law tells you how the rate changes, the rate of the reaction changes dependent on the concentration of the reactants. So how do you find a rate law? A rate law must be determined experimentally or by mechanism. Mechanism, something we'll talk about a few videos from now, but it has to be determined experimentally or by mechanism. So in one of the lab experiments that we're going to miss out on, we would have determined the rate law experimentally. You have to determine those things from experiment or through knowing the mechanism. Again, that's in the future, it's to come. You have to run multiple experiments to be able to compare them, but we're gonna have to do some math here. Let's do some math on paper. So here's the rate law that we just wrote. How in the world do you determine what X and Y equal? Well, I said you have to run multiple experiments. And so we're going to choose to compare experiment 1 and 2 first. You'll see why as I keep writing. The way we're going to do this is we're going to set rate 1 over rate 2 equal to K1 over K2, A1 to the X, A1 to the X, over A2 to the X, times B1 to the Y, over B1, over B2 to the Y. Yep, bloopers and all. I plug in the actual data. 0.11 molarity per second divided by 0.44 molarity per second. K1, K2, that's the rate constant for the same reaction. It's the same. So constant over constant, that's going to be 1. 0.17 to the X, 0.17 to the X, times 0.22 to the Y, 0.44 to the Y. So why did I pick experiment 1 and 2? Because in experiment 1 and 2, these concentrations are the same, so that entire term gets to cancel out. Could I have picked experiment 1 and 3 to compare? Absolutely. Could I have picked experiment 2 and 3 to compare? Absolutely. But you need to pick at least one set that's the same, one pair that's the same, so that you can cancel out something because it equals 1. So that simplifies to 0.25 is equal to 0.5 to the Y. If I'm dividing here, 0.22 divided by 0.44, when you divide two numbers that are raised to the same power, you can do that. So how the heck do I solve this? Well, some of you might already know the answer from looking at it without solving, but you could also write it as 1/4 equals 1/2 to the Y. That might make it easier for some of you to see as well. But really, you can solve it with logarithms or natural logs. It doesn't matter. The log of 0.25 is equal to the log of 0.5 raised to the Y. Why would you do that? Because logarithm rules say an exponent can be pulled out front as a coefficient. So this is really log of 0.25 equals Y times the log of 0.5. Ugh, almost there. So Y equals log 0.25 divided by log 0.5. Do that actual math and you get Y equals, dun, da, da, 2. Y equals 2. So I can go all the way back up here and know that Y equals 2. My reaction is second order in B. So I'm going to need to do that again to solve for x. So I can do one of two things now. I can choose two experiments where B concentration stays the same and cancel it out just like I did A's concentration here. Or since I already know what Y is, I don't actually have to choose two equations, two experiments where B is the same because I already know B, so I won't have two variables. But I'm going to make it simpler and go ahead and choose one where they're the same. So I'm going to compare experiment, let's see, 4 and 5. Why not? So I'm going to try to squish it over here, and I'm going to put 4 over 5. So 0.22 molarity per second divided by 0.33 molarity per second equals rate constant over rate constant. We don't care. Equals 0.34 to the x over 0.51 to the x over 0.22 officially squared, 0.22 squared, but we don't care. That thing gets to totally get canceled out. So now if I simplify, I get 0.67 equals 0.67 to the x. Maybe you can even solve this one without logarithms. Take the log of both sides, pull the x out front. Log of 0.67 divided by log of 0.67. Yeah, we can go through it if we really need to, but x equals 1. So experimentally, I determined that my rate law is rate equals k times a to the first power times b squared. My reaction is second order in B, first order in A, and third order overall. Not too hard. Let's do one more. Rather than switch you back to PowerPoint, we're going to keep going on notes because we're going to do the same thing again with a new set of data for a new experiment. So the first thing that needs to be done is write the generic rate law. Rate equals K times the concentration of reactants raised to some coefficient, raised to some power, that's what I really mean, times the next reactant raised to some power. The problem is these powers can only be determined through experiment. So if I look at my experimental data, I have only run 3 experiments. So I have a little bit of a challenge with how to figure out this one. I must compare experiment 1 and 2 in order to get my equation simplified to only have one variable. This time I'm going to put 2 on top of 1. No, I'm not. I'm going to put 1 on top of 2. Sorry. So I'm going to put the rate of reaction 1 over the rate of reaction 2. That equals K over K. Who cares? CH3I reaction 1 is 1.4 to the X. CH3I reaction 2, 0.85 to the X. OH is 0.1 to the Y, 0.1 to the Y. So I get to cancel out this guy. And I simplify. I encourage you to try the math and make sure you're following along with what I'm doing rather than just seeing what I'm doing and say, okay, that's cool. But here's what I've got. 2.71 is equal to 1.65 to the X. Take the log of both sides. The reason I'm taking the log of both sides is so that I can pull my X down as a coefficient. So then X equals the log of 2.71 over the log of 1.65. So when you simplify that, you get x equals 2. You officially get x equals 1.99. That's 2. So this time, since we know that x equals 2, we don't have an experiment where the CH3I, that's called methyl iodide, we don't have an experiment where methyl iodide stays the same. So we're going to have to make sure to fill in our x value. It just makes us have one more math step, but that's okay. We can do that. We can compare experiment 1 and 2, 2 and 3, 1 and 3. It doesn't matter. We'll do 1 and 3. So if I do 1 and 3, that's 15 divided by 15.31 equals K over K. I'm putting it there just so that you don't forget that that's part of the deal. And then 1.4 to the 2 divided by 1.0 to the 2 multiplied by 0.1 to the y, 0.2 to the y. Simplify my math and I got 0.979, really 0.98 equals 1.96 times 0.5 to the y. So I need to divide by this first, 0.98 divided by 1.96. That's 0.5 equals 0.5 to the y. Again, hopefully I don't need to do logarithms to see that y equals 1. So then I have my whole experimentally determined rate law is rate equals K times methyl iodide squared times hydroxide to the first power. This is my given rate law. It's a third order overall reaction. Yeah? Let's do it.